And so we begin Chapter 5. Chapter 5 deals with gases. We've talked about gases before, but this chapter is completely dedicated to them. We're going to focus generally on the behavior of substances that exist as gases under normal atmospheric conditions, which basically is defined as 25 degrees Celsius and 1 atm of pressure. All right, let's get started. This is figure 5.1 from your book, and it shows the elements that exist as gases at 25 degrees Celsius and 1 atm. The noble gases, the ones that are in group 8, are monoatomic, okay, and the other ones exist as diatomic molecules. It's important to note that there are some compounds that do exist as gases naturally, and these are shown in table 5.1. For example, nitric oxide or carbon dioxide or carbon monoxide. Those are all naturally existing as gases. Ionic compounds do not exist as gases at 25 degrees Celsius and 1 atm because cations and anions in an ionic solid are held together by very, very strong forces, electrostatic forces. So you have to basically overcome these attractions between the positive and the negative charge by applying a large amount of energy or heat. So what you would do is you melt the solid. For example, NaCl, which is table salt, melts at really high temperatures, 801 degrees Celsius. Whereas ionic compounds boil at really high temperatures, molecular compounds, which are usually liquids, boil at much lower temperatures than ionic compounds do. You need to be able to describe the general properties of a gas. For example, gases assume the volume and shape of their containers. They are the most compressible state of matter, so you can squeeze them much more than you can squeeze a solid. Gases will mix evenly and completely when they're confined to the same container. They don't separate themselves sort of like a oil and water would do. Gases mix evenly, and gases have much lower densities than liquid and solids. Section 5.2 talks about the pressure of a gas. We humans have adapted so well to the pressure of the air around us that we're basically unaware of it. But gases exert pressure on any surface with which they come in contact with. Atmospheric pressure is the pressure exerted by the Earth's atmosphere. The atoms and molecules of the gases in the atmosphere are subject to Earth's gravitational pull, just like everything else on Earth. And as a consequence of that, the atmosphere is much denser near the surface of the Earth than at high altitude. So for example, that is why they have to pressurize the cabin of an airplane, because the air outside of the cabin is way too thin for us to breathe. And as another example, if you have ever visited Denver, Colorado and have tried to exercise there, it might have been a lot more difficult than it is here. And that's because the air is a lot thinner up there, so your lungs have to work a lot harder to get the same amount of oxygen into them. And as you can see here, the density of the air decreases very rapidly with increasing distance from the surface of the Earth. And of course, not surprisingly, the denser the air is, the greater the pressure it exerts. So for example, I had a lot more pressure on me in Miami, Florida than I have if I lived in Denver, Colorado. You are going to be responsible for understanding the concept of gas pressure and converting between the common units of pressure. For example, atm, torr, millimeters of mercury, psi, pascals, and kilopascals. Pressure is one of the most readily measurable properties of a gas. In order to understand how to measure it, it's helpful to know how the units are derived. So pressure is defined as the force applied per unit area. The SI unit of pressure is the Pascal, and that's defined as 1 Newton per square meter. Well, what's a Newton? A Newton is 1 kilogram meter per second squared. A Newton is roughly equivalent to the force exerted by Earth's gravity on an apple. So how do we measure atmospheric pressure? Well, we do it with a barometer, and I'm showing you a picture of it on the right. A simple barometer consists of a long glass tube closed at one end and filled with mercury. Then you carefully invert the tube in a dish of mercury so that no air enters. This is really difficult, but some mercury will flow out of the tube into the dish, creating a vacuum at the top. The weight of the mercury that remains in the tube is supported by atmospheric pressure acting on the surface of the mercury in the dish. So standard atmospheric pressure is defined as the pressure that supports a column of mercury exactly at 760 millimeters or 76 centimeters at 0 degrees Celsius and at sea level. So in other words, that's why the conversion between atm and millimeters of mercury is 760. So how do we measure the pressure of gases other than atmosphere? We have these things called manometers, and you can see a picture of them on page 178 of your book. There's two types of them. One that measures the gas pressure of a gas that's less than atmospheric pressure, and the other measures the pressure of a gas that's greater than atmospheric pressure. Next thing I want to talk about are the gas laws. Before we go on to talk about the different gas laws, I want to do a quick problem. Let's convert 295 millimeters of mercury to kilopascals. What you would do is set it up like a dimensional analysis problem. So we know that 1 atm is equal to 760 millimeters of mercury. So we put the 760 on the bottom to cancel it out. And we also know that 1 atm is equal to 101.325 pascals. This is in your book. I would suggest you start becoming familiar with these units. And then all you got to do is convert from pascals to kilopascals. And I know that the base unit is pascals, so I changed the base. I put 10 to the third on the bottom and 1 on the top. I end up having 0.0393 kilopascals. All right, let's move on. The first law I want to talk about is Boyles Law. Robert Boyle studied the behavior of gases in the 17th century. He studied them systematically and quantitatively. Basically, what he noticed is that the pressure of a fixed amount of gas at constant temperature is inversely proportional to the volume of the gas. Here I'm showing you the apparatus that Robert Boyle used to study the relationship between pressure and volume. In the first one, the levels of mercury are equal and the pressure of the gas is equal to the atmospheric pressure, which is 760 millimeters of mercury. As an example, the gas volume is 100 milliliters. Now in the second one, he's doubling the pressure by adding more mercury, and that reduces the gas volume by 50 mils. The third one, he adds even more mercury, and you can see that the volume decreases even more. So again, Boyle's Law states that if you have a constant amount of gas and a constant temperature, the pressure is inversely proportional to the volume of the gas. So Boyle's Law depends on the temperature of a system remaining constant. But what if the temperature changes? Well, French scientists Jacques Charles and Joseph Gay-Lussac studied this relationship. And what they found out is that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to the absolute temperature of the gas. In other words, if you have constant pressure, the volume of a gas is going to decrease if the temperature is low, and the volume of a gas is going to increase if the temperature is high. A good experiment that you could do is take a balloon, blow air into it, and put it in your freezer. What happens in your freezer? It gets really cold, and you'll see, if you leave it in there for a couple of minutes, you see that it shrinks and it shrivels up. But then you take it out of the freezer and it'll go back to its exact size that it was before. So again, as you decrease the temperature, you decrease the volume of a gas. As you increase the temperature, you increase the volume of a gas. And that's exactly what Charles and Gay-Lussac's law states. The last law I want to talk about is Avogadros Law. We know Avogadro, and we learned at the beginning of the semester that Avogadro's number was originally determined by studies done with gases. Amedeo Avogadro was an Italian scientist, and he basically complemented the studies of Boyle and Charles. His law states that at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of the gas present. In the picture, I'm showing you the volume relationship of gases in a chemical reaction. The ratio of the volumes of molecular hydrogen to molecular nitrogen is 3:1, and that of ammonia, which is the product, to molecular hydrogen and molecular nitrogen combined is 2:4 or 1:2. According to the law that Avogadro states, we see that when two gases react with each other, their reacting volumes have a simple ratio to each other. If the product is a gas, its volume is related to the number of the reactants by a simple ratio. We're going to do examples later on that show this law in action. The next thing we're going to talk about is the ideal gas equation, which is PV equals nRT. PV equals nRT is basically a combination of Charles' law, Boyle's law, and Avogadro's law. And I'm going to show you a very easy way to remember each law. But that'll be in the next video. All right, see you later.